Hello, this is a short video on causal graphs, and it's part of my course on causal graphs, which I'll give you a link to. So causal graphs are a tool to help you understand your hypotheses, to express your ideas more clearly, to discover connections with other work, and design better experiments and better statistical analyses. In essence, causal graphs are very simple. They're just a mathematical language which helps us think clearly. They involve a load of circles called nodes and edges or arrows that connect them. And the meaning of an edge, so if we have a node x and a node y that are connected by an arrow, the meaning of that arrow is that if we were to change x in some suitable way, then y would also change. And this change could be deterministic or statistical. The variables could be continuous or categorical. All we're saying is that this is our hypothesis about a world. X affects Y and Y affects Z. Let's put this in a bit more of a real context. So if we imagine the relationship between the temperature, how much ice cream is being consumed by the general population, and how many shirt stains we observe. So we could say that we hypothesize that high temperatures cause more ice cream consumption, and more ice cream consumption leads to more shirt stains. And here's a causal graph, a picture that expresses that description. The interpretation of the picture is that if we manipulated temperature in a suitable way, if the temperature were to go up suddenly, then ice cream consumption would also go up. That would change. And the amount of ice cream being consumed, if that goes up, then the number of shirt stains goes up. Note that there's not an arrow from temperature to shirt stains. So this graph means that we're assuming that changing the temperature doesn't affect shirt stains except for the effect of ice cream consumption. So if we really had a hypothesis the way a temperature affected shirt stain, then we could draw that in with an extra arrow. The point is that this expresses a hypothesis about the world. It's not a statement about what is true in the world. So we could, for example, have the arrows running the other way, where if you were to stain someone's shirt, that would cause them to eat ice cream, which would increase the temperature. This seems like a really bad model of the world, but we can still express it. It's still a perfectly consistent causal graph. The idea of using this in research is to try and create causal graphs that express our hypotheses about the relationships between things in language and culture. So for example, here's a paper by Abels and Vogt, who suggest various relationships between subsistent style and the modes of speaking. Expressing your hypotheses like this, the idea is that you're more explicit about what the relationships that you're looking for are, and you can break your studies down to study one of these causal links at a time rather than try and study everything at once. So causal graphs, we can start looking at ideas of intervention and not just observation. We can think about confounding. Which variables should we control for? Drawing things out like this helps us think about that. And we can also think about spurious correlations and how to deal with colliders. I go into a lot more detail on this in my course, but I wanted to cover colliders as a way of expressing the usefulness of causal graphs. So, first of all, what is confounding? Well, the causality follows the arrows. Let's say that we're interested in the relationship between x and y, and we know that there are relationships with other variables like this causal graph. We're interested in this red relationship and causality, so if we were to change x, then y would change. If we were to change y, then according to this model, the x wouldn't necessarily change. However, observational correlation, so non-causal information, flows in both directions. which means that there's a non-causal path from x to y that goes around this way. This means that even if there was no causal link between x and y, we still might expect to see observe a correlation between x and y because of this common cause back in time. So this is a common thing. There's a confound. We need to control somehow for these two things in order to be sure that any correlation that we observe is only due to this causal effect and not due to this non-causal path. One way to do this is to use intervention. So we intervene on a variable, we go up to a variable and manually manipulate it in order to break the causal link between this other variable and x in order to stop the non-causal flow from going around. A typical way of doing this is a random control experiment. So here's an example. Let's say that we're interested in the effect of taking a particular medicine on your health. Now we know that your age will also affect your health. The older you are, the more likely you are to be ill. But you might also suspect that how old you are, the older you are, the more likely you are to forget to take your medicine. So now we have causation follows the arrows, so we're interested in the effect of taking medicine on health. But there's a non-causal path from taking medicine to health that goes through age. So somehow in our model we need to control for the effect of age. One way to do this is to use random assignment. So we randomly pick a load of people and some of them take the medicine and some of them don't. That breaks the relationship between age, and let's say, for the sake of argument, in this experiment, we force people to take the pills. Then that breaks this relationship, and any correlation we observe should be due to this causal relationship, if this is a good, complete model of the world. Another way we could do it is using statistical controls. So we could do a regression, include age as a control variable, and that breaks the causal relationships and allows us to study the effect, or the causal effect rather than the correlational effect. So that's the idea behind drawing out your causal assumptions in order to make sure that all the statistical controls that you need are in place. However, there's another problem that many people bring up. How do we know the direction of causation? Well, often we don't. These two models where x affects y or y affects x, if we were to observe a correlation, that would be equal support for either of these models. We couldn't tell the difference between these models just based on a correlation. However, when we look at three variables, things get a little bit different. So here's a few different models for the relationship between three variables x, y, and z. It could be causality flowing from this direction, from left to right, from right to left. Z could affect both x and y, or x and y could both affect z. If we think about whether we would expect x and y to be correlated in each of these cases, in the first three cases, we would expect them to be correlated. For example, in this case, changing z would change both x and y, and so x and y would be correlated to some extent. However, in the fourth model, we wouldn't expect x and y to be correlated. Here you can change x, and that will affect z, but it won't affect y in any way. So this is already interesting that we might be able to tell the difference between these three and this one. But the most interesting thing is what happens when we control for z. So if we're looking at this observation and we controlled for z either experimentally or statistically, we'd expect to break this causal link, and so that x and y would not be correlated. And the same for these other two models. However, with this final model, we would expect it to be correlated. which is a very different type of behavior. So we might be able to tell the difference between these types of causal systems and these ones. And this type of causal system is called a collider. And to understand why this happens, I'm going to use another example. So let's imagine that we're both working at a water treatment plant, and it's our job to turn these levers to control the flow of water, and the water comes out of this pipe at a certain rate. So we can measure that rate, and the rate of water coming out is Z. The flow of water from my side is X, and the flow of water from your side is Y. So I can turn my lever up and down independently of you, and that will affect Z. What I do doesn't have any effect on what you do. But now let's say that we control for Z. Our boss comes along and says, okay, we need a constant rate of water, 500 gallons an hour or something. In this case, if we want to keep Z constant, if I increase the amount of water that's coming out of my side, you have to decrease the amount of water that's coming out of your side. So now, when I change my variable, you change as well. Put it in another way, if we have a causal system like this, then we would not expect any correlation between X and Y unless we control for Z, in which we would expect a correlation. So let's think about this in a real example and how it might cause problems. So let's think about, we're looking at different words in English. And we're looking at whether the length of a word affects the reaction time for someone recognizing a word. This is a very typical psycholinguistics kind of experiment. We also know that various things have been hypothesized to affect length and reaction time. So for example, the length of a word, the longer a word is, usually the less frequent it is. And this is Zipf's law. And the valence of a word, how positive or negative it is, that we know that more positive words are recognized more quickly, and they're often also used more frequently than negative words. So here's our little model of how the world works. Assuming this is a good model, then you can notice that we've actually created a collider. So length, frequency, and valence, this relationship is a collider relationship. So what does this mean? There is a correlational path from length to reaction time, but it's being blocked by this collider. So actually, in this case, we don't need to do anything to control for the effect of frequency or valence, because it's already being controlled for. This non-causal path is already being blocked by this collider. However, if we were to control for frequency, then we would create a correlation between length and valence because of the collider, which would open up again the non-causal path. So now this is a weird kind of thing, that controlling for the wrong variables can create confounds, rather than our usual idea that the more you control for things, the more sure you are that the thing you're looking at is the thing that you want to see. And this isn't a hypothetical sort of philosophical point. You can actually see this in real data. So for example, here in R, I've made some hypothetical variables that fit this model of the world. So if you were to run this code, you'd end up with variables where this model of the world was correct. Now we could run a linear model on this, trying to predict reaction time by the length of a word. And what we'd see is that there's no correlation. And that's correct. So in this world, there's no causal or correlational link between length and reaction time. However, if we were to add frequency as a control variable, now suddenly frequency is a significant predictor, but also length is a significant predictor. we've created an artificial correlation between length and reaction time by controlling for a collider. Now, of course, this model of the world is just one possible model. There are lots of different possible models, and we might be uncertain about what the correlation is, the right causal model is. And that's fine. The point is that using causal graphs helps us understand, express what those different possibilities might be and what kinds of behavior we'd expect to see in our data given those structures. So what we want is a tool that helps us keep track of all these different models, to help us draw these things and to help us spot bits of theories that might be useful to us. That's why I created the SHIELD database, which is the Causal Hypotheses in Evolutionary Linguistics database. It's mainly about linguistics, but we're opening up to other fields as well. The idea is that you can look at a particular person's hypothesis as a connection of different causal links between variables. Then you can look at whether other people have also hypothesized or tested, have empirical support for each different link. You can also look at the relationship between this hypothesis and different hypotheses and how those link together. So here's an example of using the website. You can go to this website, search for a particular hypothesis like this, click on some links and find some quotes about what evidence is available. You can see connections to other documents or explore this hypothesis in more detail. So here I've got one hypothesis and I'm going to add a second one and color the hypotheses differently. So now I can see the relationship between these two variables. I can also automatically search for other hypotheses that are connected. And I'll find this one, for example, that happens to also talk about similar things. So the idea is that you can do quite complicated things, like take two quite large hypotheses about the relationship between various things and identify the critical causal link where they disagree. And from that, you can try and see whether anyone has tested this causal link in independent tests and try and resolve the debate between two theories. SHIELD is hosted on GitHub, so there are places to discuss and update the causal graphs. Coding causal graphs is very difficult. We've had to do a lot of revisions. And the idea is that anyone can go in, revise, change, and add papers and causal graphs to the database. We've also got a load of discussions about how this is done. If you're interested in this kind of thing, I have a video course on causal graphs. I'd recommend Judea Pearl's book, The Book of Why, which is a very clear expression of the use of causal graphs. And here are a couple of papers that express it in various subfields. Thanks for listening. I'd be very happy to answer any questions that you have. Thanks.